Hello everyone, I am Bon-jae Gu, who is an assistant professor in the Department of Food Science and Technology at Gongju National University. First of all, I would like thanks to Professor Lee, who is giving me an opportunity to speak about my research in this seminar. The subject I'm going to talk about today is optimizing chemical-free pretreatment for the bioconversion of lignocellulosic biomass from Douglas-fir first-use residuals. Basically, I use 3 different non-chemical pretreatment to increase the sugar yield from Douglas-fir wood residuals. Before jumping in the research topic, I'm going to talk about a little bit about my background. So as I mentioned, I'm working at Gongju National University currently, and I mainly study about the food processing, especially extrusion processing. And my research interests are plant-based meat outlook, food upcycling, biodegradable product, and bioconversion. And then the bioconversion, that is the topic we are going to talk about in detail today. I mentioned that I'm very interested in the extrusion processing, so I just made one slide to explain that part for my introducing some background. So I worked for extrusion processing for a while, for quite a long time, from 2008 to present, so around 14 years. And then when I checked my publication, 95% of the publication are related with the extrusion processing. And with the extrusion processing, I work with the starch and protein and fiber. So for example, for starch-based product, I work with the value-added product to increase the nutrition value. So basically, I try to add more fiber and protein, because generally starch-based product, for example snack and breakfast cereal, has very lower fiber and protein content. So in order to meet the quality of the product which people like, for example, like usually high fiber content and protein content decrease the preference of the product for consumer. So I try to increase those fiber and protein, and with high value of the nutrition. And the protein-based product, so mainly I study about the plant-based meat outlook. So plant-based meat outlook, I start from 2015, and then currently also I'm working on the plant-based meat outlook a lot. And then the last one is fiber-based product. So basically fiber multiplication by using extrusion processing. So there is the topic we are going to talk about in detail today. So that is the one of the pretreatment process I use for this project. So let me talk about my research from next slide. For the research, the research objective were to develop and optimize a milling stretch with different milling process with lower energy consumption for the wood fiber, and to make the high sugar yield. And then second one is to understand the impact of the extrusion process variable, include the screw profile, feed moisture, and then temperature on the lignocellulosic biomass on sugar yield. And the third, the study the effect of the direct steam injection pretreatment for lignocellulosic biomass, and determine the parameter that can improve the enzymatic hydrolysis. So I'm going to talk about some brief introduction about the research. Energy demand around the world is increasing because of the development of the industrial area. So we have two options to choose which energy resource we can use. The first one is non-renewable resource, and the second one is a renewable resource. So the non-renewable resource is fossil fuel such as crude oil or natural gas or coal, but they are limited resource and then they are not environmental friendly. However, the biomass or wind or solar, hydropower, geothermal are unlimited resource and they are eco-friendly energy. So we have several options to choose which raw material we can use for making the biofuel. So corn is main source for bioethanol in US, but the corn causes soil erosion, and in order to use bioethanol for all of the automobile, 97% of US land area should grow the corn feedstock. So actually, 10% of the ethanol is already used in the gas station. So basically, you need to add 10% ethanol always. It depends on where you are because it depends on the state. But Washington State, where I was, need to contain up to 10% ethanol for all gas. And then we have the other option, the lignocellulosic biomass. They are low cost and then practical alternative source. So if we see what is the difference between the woody biomass and cornstarch, the cornstarch is more softer. So basically, wood biomass is denser and then high lignin content. So it has more strong structure, and then it causes the problem to degrade the structure and result in a lower sugar conversion. From the lignocellulosic biomass, in this study we used Douglas-fir wood residue, which is the byproduct after harvesting and logging. From that, we can convert the fermentable sugar, and then with that we can make some bioethanol. But in this study, we are focusing on just from the biomass to fermentable sugar. I would like to talk about why we choose the first wood residue for making the bioethanol. So in the United States, there is many forest resource we can use. For example, 750 million acres of forest land, including 514 million acres classified as timberland in the US. And there are a lot of timberland in the northwest of the Washington state. And overstocked forest land containing small diameter and then low value forest residue can generate carbon dioxide and then methane gas, causing greenhouse effect, and it may occur wildfire as well. So they are very low value material, and then we are trying to make them bioethanol to improve the value. I'm going to talk about very short time about the structure of the lignocellulosic biomass to understand the structure and then how we can get the sugar from the structure. The photosynthesis produces carbohydrate, and this simple sugar polymerized in the plant to form long polysaccharide chains, hexose or pentose. So cellulose, hemicellulose, and lignin are produced through the photosynthesis with different pathway, and the cellulose microfibril are embedded within the matrix of other polymer, such as hemicellulose and lignins. And the hemicellulose is a mix of the branch polysaccharide made up of both 5 and 6 carbon sugar links to the rigid non-carbohydrate polymer called the lignin, which form a coating that shields cellulose and hemicellulose from enzymatic attack. So in addition to serving as the physical barrier to enzyme and microbes, lignin also is a source of the chemical coproduct that can inhibit sugar conversion to biofuel. Finding a way to control lignin formation in plant is a major focus of the bioenergy research, along with developing shoot of the tool to create valuable bioproduct from lignin. But in our research, we just mainly focusing on how we can improve the sugar yield by degrading the rigid structure of the lignin. Cellulose is the most abundant polysaccharide and is also the most abundant biomass in the earth as well. And then if you see the cellulose structure, cellulose are linked by a lipid beta glycosic bond, and then we can find 40 to 50% of cellulose in lignocellulosic biomass. Let me talk about the hemicellulose. Hemicellulose is a heteropolymer made by several sugar, xylulose, mannose, galactose, arabinose. It has a random and amorphous structure with a riddle strength, and about 20 to 40% of hemicellulose is in lignocellulosic biomass. The various polymer of hemicellulose include xylan, mainly you can see in hardwood, and gluconoxylan, and then arabinoxylan, and then glucomannan. And the glucomannan you can find mainly in the softwood, and xyloglucan. And then that is the hemicellulose structure, and then I'm going to see the lignin structure. Lignin is a complex aromatic macromolecules and is a natural glue. So cellulose and hemicellulose are held by lignin, and is comprised of the cross-linked and branched aromatic monomers called monolignol. So parachromyl alcohol and coniferol and snapol alcohol. So the precursor of the lignin were produced by enzyme. Simple sugar were converted to monolignol by enzyme in the plant. And the lignin provides the stiffness of the lignocellulosic biomass for resistant against forces that cause bending, such as wind. And lignin also acts to prevent pathogen, and Y is recalcitrant to degrade. And you can see there the red box, and that is the coniferol alcohol, which is the main the monolignol in the softwood, which is around 90 to 95% in the softwood, and 20 to 35% of lignin is in the lignocellulosic biomass in general. I'm going to talk about the main project goal in this slide. With the lignocellulosic biomass, we are trying to convert sugar by using enzymatic hydrolysis. But without any pretreatment, we can get lower sugar yield, and it requires a very long time to get the sugar with the hydrolysis, enzymatic hydrolysis. So if we choose to use some pretreatment, we can increase the sugar yield with decreasing in the hydrolysis time. And there is several different pretreatment we can choose, but in this study we use physical pretreatment, which is non-chemical pretreatment. In this slide, I'm going to talk about the mechanism of the pretreatment. It's quite simple. So cellulose is entangled by the hemicellulose, and they are covered by lignin. So without any pretreatment, the enzyme is very hard to access into the structure, but after pretreatment, they have more space where enzyme can attach, and it can increase the hydrolysis, the yield of the hydrolysis. So in order to improve the enzymatic hydrolysis, we can decrease the crystallinity of the cellulose, or we can change the structure of the lignin, or we can remove the lignin or hemicellulose, or we can depolymerize the hemicellulose entangled with the cellulose, or we can increase the surface area or porosity. These methods we can use can improve the enzymatic hydrolysis. Based on the above the method I mentioned in the previous slide, we choose 3 different methods to improve the sugar yield from the wood residue. So we use milling process and extrusion and direct steam injection to improve the enzymatic hydrolysis. As I mentioned, I use 3 different methods: milling and extrusion and steam. They are thermomechanical processes, so they are on non-chemical pretreatment. So from next slide, I'm going to talk about each process in detail and with the result. The first process I'm going to talk about is ball milling. So the ball milling uses the impact energy caused by balls, and then the wood fiber in the jar was ground. So I use that the ball milling. So the machine I have had 4 jars, and then each jar had 3 different sides of the balls. So you can see the diameter of the balls, 6 and 10 and then 20 millimeter. And each ball had different number. So 4,100 and then 10, 1,000 and then 15 balls. And the rotator, they had 1:2 or -2 rotation ratio, which means the top of the jar, the disc, so we have disc and the jar. So disc rotate 1 rotation, and then the jar under the disc rotate 2 times with different direction. So basically, when the disc, the bottom disc rotate 1 time, the jar on the top rotated 2 times. The second process was the extrusion. So there is the picture of the extruder with conveyor belt, and there is the picture when you open the extruder, and then there is several different type of the extruder, but our extruder was the clamshell type. So basically we can open the barrel like clamshell. So the maximum capacity of the motor was 7.5 horsepower, and maximum torque was 80 Newton meter, and screw speed was 250 RPM. So screw is one of the important part of the extruder, and you can see there are several different screw elements at the bottom of the picture, and then the top of the picture that you can see 2 different shaft. So basically you can use the shaft to So you can decide which screw element you want to use for your experiment, and then you can choose the screw element. You can insert the selected screw element into the shaft, and then you can design the screw element based on your research purpose. So that is one of the example of the screw element design. So we usually say that is screw configuration. So there is two shafts, as you can see in the figure. The one shaft is the bottom of the top of the barrel. So they are already set some screw design, and then you can see the middle of the picture. There are several different screw elements, and then you can decide which element is better for your research, and then you can insert them into the shaft. And then after that, you can insert the screws into the motor part, and then you can close the clamshell type of the barrel. This is the direct steam injection system. So the left side figure, that is the direct steam injection system, and then the direct steam injector is just one of the part of the system. So let me explain this system. So first, the steam is follow the pipeline, and then the green arrow mean where the wood fiber move, and then the red circle one, that is the direct steam injector. So these two material are meet at the point, and then when they meet, there is some heat exchange, and then the material move out following the blue arrow. So when you close up the red circle, so you can see the steam and wood fiber meet at the point, and then discharge following that direction. So after pretreatment process, the milling, extrusion, direct steam injection, we analyze the pre-treat sample, and then treat enzymatic hydrolysis to increase the sugar yield and check the sugar amount. From this slide, I'm going to talk about the result of the research. We use 3 different milling for enhancing the energy efficiency. So basically, we mill the Douglas-fir wood residue with the hammer milling as a coarse milling. After that, we get some powder, and we use air crucified milling as an intermediate milling. After that, with the powder, we use a ball mill for the fine milling. So for ball milling, we use 5 different milling time, which were 7, 8, 10, 20, and 30. And then you can see the different energy consumption from this slide. So basically, when you increase the ball milling time, obviously you can see the higher energy consumption. So one of the advantages to use ball mill is you can decrease the crystalline lesion of the cellulose. So cellulose has 2 different regions. You can see there in the slide. They're called as amorphous and the crystalline lesion. So basically, crystalline lesion is well ordered, and however, the amorphous is not organized well. So you can see the crystalline looks like uncooked spaghetti, or you can see the intermolecular bonding. However, amorphous, you can see it looks like the cooked spaghetti, and the large number of the hydrogen bond site are available. So basically, enzyme has more space they can attach. So amorphous region is more accessible, and the crystal region is inaccessible when we compare between the region. You can see the effect of the bone milling on crystallinity of the cellulose in this slide. So you can see the red line, which is the control sample, and it shows the crystallinity index of 40.7%. However, when the bone milling time increased from 7 to 30 minutes, the crystallinity index decreased down to 11.7. And also, obviously, you can see the decrease in medium particle size from 121.33 micrometer down to 14.87 micrometer. This slide shows the correlation metrics for bone milled residual. Based on the research, we observed the crystallinity index and the medium particle size had a strong negative correlation with sugar yield. So basically, when crystallinity index and particle size decrease, you can see the increase in the sugar yield. And as I mentioned in the previous slide, you can see the increase the sugar yield by increasing the bone milling time because of the increase in the energy consumption of the bone milling. So, but the problem is the energy efficiency to make the glucose, and then bone milling 7 minutes had the highest the energy efficiency compared to the other bone milling time. So we can find the higher energy consumption cause the higher sugar yield, glucose and xylulose mannose yield. Overall, the major conclusion was the first one was the crystallinity index of the cellulose was decreased through the bone milling, and crystallinity index and medium particle size had a negative correlation with sugar yield. And the last, the higher energy consumption led to increase in the sugar yield. That was the first conclusion. And then from this slide, I'm going to talk about the result of the extrusion process. That is the diagram of the extruder. So you can see the feedstock from here. We use the wood fiber, right? So wood fiber load into the hoofer, and then the fiber is followed by the screw in the battle. And there are heater to increase the temperature of the battle. And the sample is squeezed out from the nozzle, and then that is the extruded sample we can get from the extruder. So if you see the sample from the extruder, we can see the flour basically. And then when you load the sample, it's also flour. But if you see the sample with scanning electron microscope, it looks like similar with the ice, but actually it has a big change. So after extrusion, you can see there many sites are open because of shear energy. The shear energy is the most important energy of the extruder, and they are related with it is related with the torque and the specific mechanical energy input. So the x-axis of the figure mean the torque and the specific mechanical energy input A and B respectively, and then y-axis mean the glucose xylulose mannose yield, and then the square shape is glucose yield and the round shape is xylulose mannose yield. So basically, when you increase the torque or the specific mechanical energy input, and you can get the higher sugar yield, so they are very strong correlationship. So if you see the correlation matrix for extruded residual, the sugar yield, glucose, and xylulose mannose yield had very strong correlation with the specific mechanical energy and the torque value. So basically, when you increase the energy, and you can get high sugar yield. So this slide shows the effect of the extrusion process. So you already saw this figure in the first slide of the extrusion part. So left side is the non-extruded sample, but with the extrusion process, you can see the change of the wood residual. So with the bare eye, without any equipment, when you see the sample between the raw material and extruded sample, actually you cannot find big difference. But as I mentioned, with the scanning electron microscope, you can see the big change between two samples. So because of the shared energy, the structure of the fiber is destroyed, and you can see the more open site where enzyme can attach and degrade the cellulose structure or hemicellulose structure as well. So the major conclusion of the second part is the extrusion imparted the physical and structural change in the wood residual, and it results in increased the sugar yield. And then specific mechanical energy and torque had a very strong positive correlation with the sugar yield. And let's see the third part of the pretreatment, which is direct steam injection system. This slide shows the flow chart of the multiple step process that I use for enhancing the enzymatic hydrolysis. As we mentioned in the previous slide, the ball mill, extrusion, direct steam injection are utilized to increase the sugar yield. So direct steam injection system was the last step for the multiple step. So as I mentioned in the previous slide, the steam and wood slurry meet at the direct steam injector, and they are discharged, and then I call the sample as DSI sample, which is direct steam injection sample. If you see the mechanism of direct steam injection, the left side figure means the sample that has already destroyed by the ball mill and extrusion. And we add some water to make some slurry, wood slurry, to use the steam injection. So as you know, the volume of the water has more lower volume compared to the steam. So when the water had some phase change into the steam, you can see the volume increase. Then the hypothesis was the higher volume, because of the phase change, can degrade the structure of the cellulose or hemicellulose, and then the degradation can help to increase their sugar yield. This slide shows the effect of the direct steam injection. So I had three different sample control, T50, T200. So the difference between the control and then T50, T200 are control sample is extruded, non-extruded sample. So basically they are not extruded, but T50 and T200 mean they are extruded at 50 degrees Celsius and 200 degrees Celsius. So the meaning of the 50 degrees Celsius to 100 degrees Celsius is the better temperature, not the steam injection temperature. So the control sample, non-extruded sample, had the increase in the particle size, but they are not significant different. And then the T50 and the T200 sample that are extruded sample, has decreased in the particle side, and then it was significantly different. And then if you see the sugar yield, the glucose and xylose mannose yields, there are non-significant difference observed. So basically, especially glucose is some of the sample is increased, but some of the not, and the xylose mannose yield as well. There's some change, but was not significant different. The major conclusion of the third step with the diasteme injection system. So particle size of the extruded wood residue after diasteme injection was decreased, while non-extruded wood residue was not. And then improvement of the high and adequate glucose and xylose yield was not observed with the additional diasteme injection treatment step. Let me talk about the overall conclusion in this slide. So combination of the milling process with the bone mill was shown to be a potential pretreatment for lignocellulose biomass for energy efficient conversion. And then second one is extrusion processing. So extrusion processing can be an effective pretreatment method to help open up the structure of the wood residue, leading an increase in the access of cellulose for enzyme. And then diasteme injection did not significantly improve enzymatic hydrolysis of the cellulose biomass within the condition we study in this project, but more study is required for figuring out the best condition for diasteme injection. Thanks for listening, and that is all I prepare in this seminar. And if you have any question, you can send an email or leave a comment. And if you find more information about me, you can find me through the LinkedIn.